Here we're going to look at hypothesis test when sigma is unknown. Since S is an estimate for sigma, we now estimate the standard deviation of the sampling distribution of sample means to be S over the square root of n rather than sigma over the square root of n. Your test statistic for t is t equals x bar minus mu divided by S over the square root of n. We have n minus 1 degrees of freedom, so your sample size minus 1. We use that when we look it up in the table, in the t table. If you compare that to when sigma was known, so when they told you that the population standard deviation was a certain number, that's when you use the z distribution. Now notice that these are the same formula except z instead of t, and when you know sigma, you use sigma rather than s, and vice versa. Okay, so that's the only difference. Okay, so number one, we have a sample of 30 cereal servings, a mean sodium content of 226.9 milligrams. So mean sodium content of 226.9 with a standard deviation of 10. So when you read this, those statistics are coming from the sample. So 10 is S, 30 is your N value, your sample size. Can the cereal maker conclude that the mean sodium content per serving is less than 230 milligrams at a 0.01 level of significance? So that level of significance, that's your alpha value. And it asks, can you conclude that the mean content per serving is less than 230? So they're trying to claim that the mean, mu, is less than 230 milligrams. Okay, so that right there allows you to set up your hypotheses. And from this point on, it's essentially the same thing as we've done before, except now instead of z, you're using t because you're given the sample standard deviation rather than sigma. But the steps for the hypothesis test are still the same. You set up your hypotheses, you create your rejection regions, you find your you collect your data, you calculate your test statistic from that data, and then you make your decision about HO, the null hypothesis. So same process as before, the only difference is now we have to worry about the t distribution. Okay, so I'm just going to show the answer here and I'll explain part of what I wrote. But when you write the hypotheses, okay, we've done that before. You set up your rejection region. Now the only difference is we're using t instead of z because we have the sample standard deviation. So you can see negative 2.462. Now where does that come from? Remember that you set up your rejection region based on your level of significance or your alpha value. Okay, that was the probability of a type 1 error. So here we have a 0.01 alpha and we're in one tail. Because of the less than, we're just in the left-hand tail. So on our t distribution, okay, on this one that I'm using, it says one tail and two tails at the top of it. Some of them, some of the textbooks and tables will have that on the bottom, and then it'll have the confidence level on the top. This one just does it backwards from that. Okay, it's fine. You still get the same numbers for them. You still use it the same way, just where you look is a little different. Okay, so here we have alpha was 0.01, and our sample size was 30. So that means we use 29 degrees of freedom. Okay, so we have 0.01 in one tail. Okay, because we shaded to the left-hand end. Okay, so when you look at how we shaded that, it's on the left-hand end in one tail. Now, even if that said greater than, we would be shaded to the right instead of left, and that's still one tail. The only time you use the two tails is when it says you're different from or not equal to when you're in your alternative hypothesis. If that was not equal to there, then you would use two tails. Okay, so we go to 0.01 in one tail, 29 degrees of freedom. So we scroll down to 29 degrees of freedom. Okay, so right here, and we see we get the 2.462. We use negative because we're on the left-hand side. So zero's in the center, remember. So negative 2.462 is your cutoff for the rejection region for the null hypothesis. Okay, so we calculate the test statistic. Again, the same idea as before. Your sample mean minus the hypothesized mean divided by S over the square root of n. and we get negative 1.698, which we can see is not passed to the left of negative 2.462. So basically saying that if the mean really were 230 milligrams, then the sample that we collected of 226.9 would not have been unusual enough to say that that mean was wrong. Okay, so our decision about HO is to fail to reject HO. Okay, we're not in the rejection region here. And what does that tell us about the alternative? If we fail to reject HO, that means we cannot support the alternative. Okay, so not enough evidence to support the claim that the mean sodium content per serving is less than 230 milligrams. Okay, moving on to the next one. Okay, again, you can set this up. Oops. Okay, you set it up, and let me get up there so you can see it. Okay, so you set it up, and I will show the answer and explain a few things in it. But remember, same thing, set up your hypotheses, find your test statistic, create the rejection region, and then make your decision. Okay, so I'm going to show you the answer. Okay, here's your hypotheses. Again, that should be easy for you to set up at this point. Our rejection region, we have a greater than, mu is greater than 4.5, so we're shaded to the right. With alpha is 0.05, so we have 0.05 in one tail. And our sample size, we had 81 college students, so that's 80 degrees of freedom. So when you scroll down to the 80 degrees of freedom, that gives you the 1.664. Okay, so that gives you, where was it? Right here. Okay, so you can see that was the 0.05 in one tail. Okay, so that's our rejection region. Our our test statistic was 1.227, which was not past the 1.664. So if the mean really were 4.5, it would not be unusual to get that test statistic of 1.227. So just like on the last one, we failed to reject HO, and there's not enough evidence to support the claim because the claim is the alternative. Not enough evidence to support that claim that mu is greater than 4.5. Okay, the next one, test the claim that the mean time for all college students is different from 4.5. Well, now the key word here is different from, which means not equal to. So that'll change your hypotheses, but everything else is still the same idea. So take a minute and do that, and I'm going to show you the answer. Pause the video. Okay, so here's the answer. We have our hypotheses set up. We have the rejection regions. Here, alpha was 0.05. Because it's a two-tailed test, because different from means not equal to for the alternative. So you have to split it to the two tails. So take that 0.05, divide it by 2, you get 0.025. So what you're going to be using here is the column that has in one tail, it has 0.025, and in two tails, it has 0.05. Okay, so there's a total of 0.05 and 0.025 in one tail. Okay, so then when you scroll down, again, you have 80 degrees of freedom, and you get 1.99. Okay, so we have plus and minus 1.99. Okay, now, again, in theory, you haven't collected your data yet, so this is where we're going to reject HO if we're beyond 1.99 on the positive side or negative side. Okay, so right now, we're not sure if it's higher or lower. So you collect your data, and this is what happened. We ended up with a test statistic of 1.227, and notice that's the same as before. Nothing changed from the previous one. You're still plugging in the same values. The only different thing now is the rejection region. Okay, so we end up still failing to reject HO, not enough evidence to support the claim that mu is not equal to 4.5. Okay, and then the last couple here. Okay, I would suggest you read that. My alpha value, I misprint on here. It's correct on your paper, but 0.025 significant level. Okay, so read that. Pause the video and I'm going to show you the answer. Okay, so this one, you end up with a test statistic of 2.491, which ends up being to the right of 2.042. Okay, so that 2.042, if you look up 0.025 in one tail, okay, so 0.025 in one tail, and then down to 34 degrees of freedom. Okay, so you have to go to the 30 degrees of freedom to get the 2.042. Okay, and then in this case we reject HO because our test statistic is in that rejection region. So if the mean was really 65 miles per hour on that stretch of road, then it would be unusual to get a sample mean of 67.4 if 65 was really the mean. Okay, so our test statistic is beyond the center where we expected it to be. Okay. So then, at what significance level would the claim not be supported? So I ask you this so I can show you in the table how it kind of works. Okay, so our test statistic was beyond 2.042. In order to not support the claim, we'd have to reach the opposite conclusion here, where we would fail to reject HO. We don't fail to reject HO until that critical number, that T star value, is beyond the test statistic, or the test statistic is to the left of, or on the other side of, in this case, 2.042, okay, or the critical number. So when you look at the row where we found the 2.042, our test statistic was 2.491. Okay, so when do we go beyond that? 2.491? Well, 2.457, we haven't gotten there yet. And then 2.750, that's beyond our test statistic. So the first time that we would do the opposite conclusion where we reject HO is, if you scroll all the way up, in the one tail when alpha is 0.005. Okay, so that's the first time that you would reject HO, because then this critical number here moved beyond your test statistic. That'd be the first time. Okay, so when alpha is 0.005. Okay, so that's the first time in that 30 degrees of freedom row that you end up with a T value greater than 2.491. Okay, then moving on to the last one. What would you guess the mean GPA of all CCC students is? Now, I'm just saying 2.0 because that's about what a C average is. I don't know this. Maybe CCC stands for we're C students. I don't know. That's a joke. All right, so test that claim, and you could use it. You could say 2.5. You could say 3.0. You could use 1.2. Okay, whatever you use there, I'll show you how that changes in your answer when you do the test here. Okay, I'm just going to use 2.0. Okay, so test the claim that the GPA of all students is different from your guess. The GPA of a simple random sample of CCC students is given below. And we're going to have to choose our own alpha value. Okay, now generally you can just go with an alpha value of 0.05 or 0.01. Okay, that's really just up to you. But you should determine that before you collect your data, or before you perform the test. Okay, so we're given this simple random sample of 16 CCC students. So now what's different here is you need to calculate the sample mean and standard deviation yourself. Okay, so when you have a list of data, you need to do that yourself. Put them in list 1, do the 1-bar stats, and you find your X bar and S. Now your calculator does give you a sigma, but remember your calculator does not know that this is not a population when you entered it in your list. So you need to be smarter than the calculator and know that it's a sample. So you're going to use S. Okay, so our hypotheses, or let me backtrack. You should get a sample mean of 2.51375. Now I'm not going to round that just because those numbers are pretty small and the standard deviation of 0.764, that's what S is. You don't want to round too much, so I'm just going to leave that X bar where it is. And I did round the sample standard deviation to 0.764. Okay, so you set up your hypotheses. Now, if you said 3.0 up here, then you would just say mu equals 3.0, mu not equal to 3.0. Okay, and then you find your rejection region. Okay, so your rejection region, you have, I'm using alpha's 0.05, so in two tails, I get t-values of plus or minus 2.131. Calculate your test statistic, and you get 2.69. And again, with the rounding, it might be a little bit different. Your test statistic for me, that 2.69 came from me using 2.0 for the null hypothesis, for the mean. Okay, so mine ends up being farther to the right in the rejection region. So my decision would be to reject HO, and there's enough evidence to support the claim that the mean GPA is different from 2.0. If you guessed like 2.5, then 2.51375 minus 2.5 divided by your standard deviation over the square root of n, that's going to be a very small t-value, like point something. Okay, so that would mean you would fail to reject HO. Okay, so the closer you are to 2.51375 for your guess, then the more likely you are to fail to reject HO.